So, hello everyone and welcome back to our next session of our Digital V-Days. And yeah, today's topic is the introduction to thermal aging in molded inductors. And I'm very happy to welcome here with me Jose and Carlos Farnos. And yeah, thank you very much that you are part of this. And yeah, so just some information from my side before we start into the session. You will be muted during this webinar, so if you have any questions, then just just use the chat. And after the presentation of both of you, we will go into the live Q&A. And yeah, also we will share the handout with you at the end of the presentation. So yeah, and if you have any questions left, then just email us at digital-v-days@we-online.com. Okay. So I think that's enough from my side. I wish you an exciting webinar, and for both of you, have fun and yeah, a good webinar.
Thank you. Okay, thank you for this very nice introduction. My name is Carlos Farnos. I'm together with Jose Roncamora, and today we will talk about thermal aging in molded inductors. And to understand this phenomena of the thermal aging in molded inductors, we will first make some review of the market trends in the power converters to see how the market pushed the passive components to its limits, and we were forced to find new solutions to match your application and your requirements. That's why we will have a review that why we move from the ferrites, as it was the main solution for most of the application, to molded inductors. And then we will focus on the characteristic of the molded inductors itself. And as soon as we have an understanding of what a molded inductor is and what are the most critical points about them, we will jump into the main topic of this presentation, that it is the thermal aging. Thermal aging is a very big topic, and in this presentation we will make just an introduction to it. So we will start with market trends, and I selected these two examples because everybody is very familiar with them. On the left side of the slide, we have the evolution of the mobile phones since the early 90s till latest. This is not the latest smartphone you can find, but you have the idea. So what we can find is at the beginning we had very big devices with very limited functions that they were only able to make and receive some calls, and with a very limited battery life. Over the decades, these systems evolved to being smaller and with much more battery life, much more efficient. And after the 2000s, much more features were added to these devices. So they are not telephones anymore, they are multimedia devices. And the last telephones are just like a small computer, super powerful computer we can find in our pocket. So there is a trend that they got smaller, they got more complex, and they are more powerful. On the right hand side, I wanted to talk also a little bit about the evolution in the automotive industry, because everybody is familiar with it. And we have the evolution of the electronic systems inside the vehicles. And these graphs start in the 1980s, where the cars were mainly mechanical systems with very little electronics inside. You can find the first fuel injection at this time and cruise control, but over the time, much more electronic systems were added into the car. We have some traction control system, extra security system like anti-lock brakes, and many other features. After 2000, we have airbag, electronic stability, adaptive cruise control. And among to these security system and advanced driver assistance system, we had a lot of infotainment displays in the car for infotainment, also for display all the information. You can see that the evolution of the complexity of the car is almost exponential over the time. And I still haven't made any mention about hybrid and electric trends we can find in the cars, or in the future autonomous driving, that it will create much more complex system that we will need to allocate dozens of different cameras, radars, and ultrasonic systems inside of the car and actuators to be able that they drive on their own. And of course, there is something important to point here, that all these systems needs to be allocated inside the car, which it is exactly the same size. So they are fighting for the same space. So in this time, the cars are not going smaller, but we need to put much more things inside.
Good. And what the market need from Wurth Elektronik? Why we need to give or to improve in our technologies? So as Carlos mentioned, the devices now requires much more system. The system need to be complex, much more complex. So that's why we need to make smaller parts. We need to have even more power density in the same functionality. So the parts need to dissipate much more heat in less space. And this will compromise, of course, the reliability. So our part cannot be under a lower qualification. So we are having very good qualification for our parts, and we give the customer a good, efficient product at the end.
So all these systems that we have mentioned, and not only automotive telephones, any industry and electronic consumer application needs to be powered. And since the early 1970s, with the introduction of the switch mode power supplies, this was the main way to power up these systems. And since the beginning, we have a very nice option for these switch mode power supplies. Talking about the inductors, I am referring to ferrite inductors. Now we will review a little bit what are the characteristics of these ferrite inductors, and what is important to point is that we need to make this component smaller, and in a DC-DC converter, in a power supply, the only way to do that is to increase the switching frequency and the operating frequencies. And we will see why ferrites are a very good option, and where are the limits of the ferrites, and when the molded inductor will jump in. Ferrites are a very nice option because they have a very high permeability, so they allow us to build inductors with high inductance, with low number of turns, low RDC. They have a good saturation behavior, and they have a very high volt resistivity that we will see later that it will be very important regarding the core losses. Also, by the time right now, this been available in the market for a very long time, and we accumulated a lot of experience with them. When we are talking about ferrites, we are talking about several different compositions like manganese thin, nickel copper thin, that can be adjusted and modified to match all the specific requirements of your application. And because they've been available for a very long time, now they are relatively economic solution. And in a very wide different option available. On the left, you have an explosion of just one example of what can be achieved with a ferrite with some outside shielding to improve the radiated emissions even.
Thanks, Carlos. So the ferrites are very good option always, and they are very well performance in high frequency applications where the frequency is going a high domain, so they have a good properties in that. Then also talking about saturation behaviors. So the ferrite also have a good saturation behavior, but when it's for one side is maintaining constant inductance until reaching one point, the saturation point, so the saturation will decrease very hard. So it is called a hard saturation. And then you will lose the inductance. So you cannot save much more energy in this construction. So therefore they need air gaps in their construction to increase saturation current. But this will reduce a little bit the permeability, and then you will reduce also the inductance. So you need to put at the end a little bit of more tons. By the way, the molded inductors, they have a better performance about saturation behavior. So the saturation is gradual dropping by the time. So they even start first earlier to saturate, but it will make soft. So once there in this graphic, we can see in one point in the black curve that the ferrite will drop, and you will not have more inductance value, but the way the molded inductor will stay having a constantly or almost constant the inductance. This will also make them, the molded inductors, very suitable for high power density application, and also we can achieve higher transient current spikes. Here we can see also a very typical property regarding saturation behavior. So in the right side, talking about ferrites, they are very dependent about temperature. So we have been testing this product from our portfolio, make of ferrite cores, and we see we have been increasing the temperature from minus 40 degrees until 150 degrees. We can see that the saturation behavior is changing over the time. Over the temperature. This is because of the properties of the ferrite cores. By the way, the molded inductors, they almost not change in regards to the temperature. By increasing the temperature, the saturation will stay always keeping in the same levels. So this makes very easy for designers to implement molded inductors in when the application is needed, need a high demand of current. We recommend you to go to our Red Expert online tool, where we make a good simulations for your application, and all these simulations is based off real data. So we measure all our parts, and we introduce there the properties and all the data by from the measurements we take in our laboratories. They will help you to designers to improve your application.
As we said in the previous slide, we have several advantages using molded inductors. And now we will see a little bit what is the main construction of molded inductors you can find in the market. The ferrite inductors are constructed in a very different way. First, you need to manufacture the core separated, and then you do the winding around, and you have some extra processes of gluing to hold everything together, some welding, and maybe you have to add some base or clip. In the case of molded inductors, you do the other way around. You prepare an air cool, and depending of the molded inductor you are doing. You need to make some solder to lead frame that later will be the terminals, as we can see in the central X-ray image of the most typical molded inductor you can find. Then the charcoal is put it into cavity fixture and is filled everything with iron powder alloy, and then is press everything together. And on the left we have a very interesting product. This is Maya or MAPI, depending if it is automotive or industrial application. And this is a very advanced and technological solution in which we don't have any sort of lead frame inside. We avoid doing this welding on the wire that could be very critical points of reliability in the long term. And the wire is done until the surface of the component, and then it is built a plating surface to grow the terminal. So the wire will be directly connected to the PCB. As I said, this is better for the reliability, but also it reduces the DC losses. So we totally recommend this part that Wurth Elektronik has a patent on it. On the right hand side, just for finishing, we have an example of flat wire inductor that is possible also to make this molded inductor construction, and the wire will come out in the bottom of the part to confront the terminal. What it is important, and compared to a ferrite, we saw in the previous slide that the saturation behavior will be better in a molded inductor. Why? Because it doesn't change with the temperature. If we want to do things smaller and with a high power application, they will work at high temperature. What it will be suitable at 20 degrees might be not at 150. Also, we are taking advantage of all the available space to allocate core material inside, so it will be better for inductance and for saturation.
Thanks.
And please, Jose.
Thanks, Carlos. Now we will talk a little bit about core losses and winding losses. About the losses, which is also the main topic of this presentation. We can divide the losses in two, in winding losses in regards to the winding, to the copper, and to the core losses in regards to the core material. So the winding losses, here we wrote ohmic losses, which is referring to the heating of the copper itself, so the thermal properties of the copper. So once you throw current to the copper, so the copper will start to heat by themselves. Then you have also the skin effect, which is dependent of the frequency, in the frequency domain. And we have also proximity effect losses, which is the currents which are around the windings. Then we have the core losses, and the core losses are divided by two. The hysteresis losses, which are depending on the different changes of the domain of the magnetic field, and with the ferrites are very good in that kind of losses. And then we have eddy current losses, which are the ones that are the main point to later to talk about thermal aging. So eddy current losses are depending on frequency as well, and they will start by high frequencies having in the core material.
So I will explain a little bit more about what is these eddy current losses and why the ferrite material was very good for high frequency application. These eddy current are induced into the material because of the variation of the flux inside of it. So it is important to mention that it is dependent to the square of the frequency. So the higher the frequency, the bigger there will be these losses. So it is very important that for these currents to be established inside the material must be conductive. And in the case of the ferrite, they have very high bulk resistivity, so we don't face this problem. In the case of the iron alloy cores, iron alloy is naturally conductive, independently of the kind of alloy we use. So if we build the core just pressing everything together, we will have a very big domain for these eddy currents to be established inside of our core, and our losses will be very high, and it will not be suitable for high frequency application. What we try to do in soft magnetic composites, we need, before building these molded inductors, we need to grow some insulation layer over each single particle of the core. So then when we press everything together and we build the inductor, eddy currents cannot flow all through the component. It will be ideally restricted to every single grain. And we are talking about grains of size of microns, of tens of microns. And why is this important? Eddy current losses are dependent on the square of the frequency, but also depending on the square of the size of these domains. So if we can make it smaller, we can counteract this frequency effect, and we can live without worries about the eddy currents. So what happens with the thermal aging? That is the main topic of this presentation. After exposing this component for high temperatures for over long periods of time, this insulation we have grow over the surface of every single particle gets degraded, and the insulation between particles is broken, and these currents are able to flow through all of them, or to a bigger portion of them over the time. This is a long-term irreversible degradation process that affects the structure, the content, and the morphology of the submagnetics. And it is important to mention that it is a permanent effect. If it happened to you at 150 degrees and then you go back to ambient temperature, the damage is done and is not coming back to normal. So as we mentioned, this process and this degradation process is triggered by the continuous exposition of high temperatures. The higher the temperature, the faster and the worse will be the effects on the component. And of course, what are these effects? The main effect, and it is related to the explanation we have just made about the eddy current losses, is that the losses in the core will increase over the time, and the performance and efficiency of your system will go down. The losses in the part will go up. Also, the operating temperature will go up for this effect, and you can face problems of thermal runaways. Just a small comment on the picture you can see on the left. This is electronic microscope picture that you can see. I will try to point. One second. You can see these are the iron alloy particles, and this is the binder. The binder that hold together all these particles together, so offers some mechanical stability, but also offers some insulation between the particles. And this insulation is what it restricts the eddy losses to grow. So what happens to this insulation when it's exposed to high temperatures is that it shrinks and it goes thinner and thinner and thinner over the time. But it is not only a thing that you can see with a microscope. It's sometimes possible to see just with naked eyes. As you can see in the picture, and I hope you can feel the difference in the color. We have on the left a fresh part just out of the reel. We did a cross section to check the inside, and on the right side we have a part that has been exposed to high temperature for a long time, and we can see some yellowish decoloration that is a symptom that something is happening with this binder material inside, because the iron alloy is not affected at this low temperatures for metals. So we know that this is a problem, and we need to be aware of it and to be able to characterize. So there are several ways to measure it. One would be, for example, putting the parts into the oven, take it out and cut it in half and measure the average thickness of this binder between the particles. What will be a very time-consuming procedure that it will be very difficult to relate them to the final electrical characteristic of the parts. Another way will be to solder the parts into PCBs to measure the AC losses. We have some workbench that simulates the behavior of a DC-DC converter. So we have the oscilloscope traces, so we can very exactly measure the losses inside the component, and then make the electrical characterization and put into the oven for some time, some temperature, take the parts out, and do this cycling process. This is a very nice procedure because you have the exact measurement of the increase of the AC losses, but you have two big problems. This is a super high time consuming, and also the parts must be soldered on PCB, so the PCB will degrade. Other way to characterize this degradation process will be to find some electrical characteristic that would be easy to measure in the components, so we can do it in a fast way, and that is related to the AC losses in the core. So, for example, we are testing inductors. The main characteristic of an inductor is the inductance, for sure. So this will be our first candidate to do this characterization. Here we have an example of a comparison of testing we did between two new release parts for the industry portfolio, two LHMI high temperature ones, as you can see in black and red. And for other competitors we selected from the market, qualified grade 0 up to 125 degrees, but also grade 1, 150 degrees. And we measure periodically the evolution of the inductance against the time at 200 degrees. And we try to figure it out what is happening with this thermal aging process with this measurement. What we can see is that there is some drift in the characteristics of the inductance for every single part, but we cannot extract any conclusion out of this measurement because all of them, they stay inside of the 20% tolerance of the part. So it would be nice to have another characteristic that can be related directly to the AC losses. And fortunately, we have this Q value, and this Q value is a representation of the total amount of energy you can store per cycle versus the energy loss per cycle. So in a perfect inductance, it will be an infinite value because you will be able to store large infinite amount of energy with zero losses. In reality, it doesn't work like that. We have all kinds of losses we have previously explained, but the higher the Q, the better the inductor, more ideal it is, and the lower losses we have. So we can do to track this thermal aging phenomena is to track this Q value over the time and to see if it changes. And now we can see with the exactly same parts we saw you in the previous slide that in this case there is a big difference between one part and the other. We can see that some part at the very beginning of the test literally dropped to 0. This is changes in percentage. So we can see for the yellow part that the final Q value is 1% of the original value. So it's 100 times worse. For the Wurth Elektronik parts, we can see that there is almost a deviation of less than 10% of value after 1000 hours at 200 degrees. and we did this measurement at 2 megahertz. And let me make some comments about this. First of all, if we are testing parts that are qualified for 150 or 125 degrees, why we exposed to this such high temperature? It's because the parts are so robust that if we test at a normal operating temperature of 150 degrees, this test will take a very, very long time. We have been running tests for a lot of parts, a lot of different conditions of temperature and time, and we saw some correlation that every time you increase the temperature 10 degrees, the test gets shortened in half. So in that case, for example, our part after 1000 hours, it had a change of 10%. If we want to see the same change at 150 degrees, it means that we shall wait more than 30,000 hours. It is quite a long time for this testing. It's almost 3 years and a half. Also, here we have Q value, but Q value is not easy losses. After testing several different products, we found some thumb of rule correlation that approximately 40% decrease in Q value equivalates approximately to double the AC losses. So in a case of 10%, we shall expect less than 20% increase on the AC losses. That is a very low value. And this is why we can very easily characterize this degradation process. For sure, all these pieces are qualified gray zero in the ECQ, and some of you might ask, why is not identified this process during the qualification? Because in the qualification, it is checked what are the electrical parameters that appears in the datasheet. If the Q value doesn't appear in the datasheet, it will be impossible to identify it. Also, some of these processes take longer time than 1000 hours to make presence, to be able to notice them. So many times ACQ is not good enough to see this kind of issues. That's why Wurth Elektronik wants to offer you some extra support to take care that you will not find any kind of long-term reliability on your designs. And other things that shall be pointed here. Does it mean that a part that has this very big degradation, is it broken? It's a good question. Is it broken? Will it stop to work? And the answer is not. If we go to the extreme result of the thermal aging, that will be there is no insulation between the particles, we will have a part that will offer some inductance, but the AC losses will be super high. It will work, but for room temperature could be switchable. If it is an high temperature environment, let's think, for example, inside in a car next to the engine, it will be super hot and you will have a thermal runaway. Another question that might come to you at this moment is how much can these AC losses increase? And we saw in our laboratories that these AC losses can multiply by 5, 6, even 7 times more than the initial value. So the risk of a thermal runaway in a long-term reliability is quite hard. In order to offer you some solutions that are capable to go over this problem, so you don't need to worry about this and worry about other things, Wurth Elektronik has released a new portfolio of products either for industrial and automotive application that, as we saw in the previous slide, up to 30,000 hours of normal operating temperature condition, you will not face any problem. And we are talking about 30,000 hours at the maximum operating temperature of the part. That normally will not be the case. It will have some mission profile that it will be sometimes at high temperature, but not forever. And even in that case, we can ensure very high reliability. And just making some mention of the different products we can offer to you. We have LHMI, high temperature, in 4 different sizes. Also, coming very soon into the market, some automotive molded inductor, LHCA, in different sizes qualified for 155 degrees. So you don't need to worry about this effect anymore. Some flat wire solution you can see in the middle, both automotive and industry version. You can see for the A at the end, it means automotive, very easy to remember. These are the sizes. In every size there is a lot of part numbers inside, and we want to make a special attention to MAPI and Maya. This very advanced and technological solution we showed you before. This wire is directly connected to the PCB with this metallization layer. It's a very interesting product, very small size, very convenient for these miniaturization trends in the market we saw before. So we really encourage you to visit our portfolio, our online catalog, and to get in contact with any of our sales representatives that will support you to select the best option for your application. And that's it. Thank you very much for attending and joining this presentation.
So, hi also from my side again. Thank you. I think also the audio is running back again. So yeah, I just shared the handout with you. I see, okay, the first ones of you are already downloading it. So yeah, there's the possibility to download the slides you just saw. But now, first of all, thank you for the cool presentation. And yeah, now we're just heading right into the Q&As. And I would start with the first question here. Are the products also available in Red Expert?
I can answer this. Yes, every product we release into the market, we prepare all this information we said to you to Red Expert. We can offer you these different saturation curves. Maybe I will go back. It will be easy if we can see it. So you can enter your temperature, your expected temperature of your application, and you can check if at 150 degrees it will be suitable for you or not. You don't need to pay so much attention if you select a molded inductor. And also regarding the AC losses, for sure, we offer all these available in Red Expert for free for every single part number we release into the market.
Okay. Carlos, thank you very much. Then we are just going to the next question. Does soldering process also degrades isolation of grains of molded inductors?
I will go.
Yeah.
Not. Because we do before we do the core. I think this will be helpful. If I have this. Okay. The first thing we do to build this molded inductor is to do this winding, this incl, and then we do the soldering to the lead frame. And after the solder, the wire is already cold. We put into the fixture, we put all the iron powder inside, and then we do the pressing. So as we do the soldering process before, it doesn't affect the core material.
Okay. Yeah, thank you very much for the next question. Yeah, then we will just head into the next one. How many reflow cycles are possible? I think that depends, but yeah.
This is the same. So we are testing for even more than 3 reflows. So we recommend also to fulfill the standard what we are having. So 3 reflows are possible. Even sometimes we test more.
Okay, Jose, thank you very much. So, okay, I see one question is coming up. I think for that we have still time. Do you confirm that if we remain below the maximum operating temperature mentioned in the datasheet, we are not concerned by this aging degradation?
Okay, I will answer this one. Let's go for example to to this one. Okay. So as I said before, just as a thumb of rule, we can say that every time we decrease the temperature 10 degrees, this time of survivance will be double. Okay, so for example, if we go to 130 degrees, that it will be a very high temperature for continuous operation. A part like this, to have some problems, it will take like 120,000 hours of operation before you can see any minimal change. And I say minimal because it's just a 10%. If we think about a car, for example, if you are driving a car for 120,000 hours at 50 kilometers per hour, we are talking about of more than 600,000 kilometers. That it is much more than the normal guarantee that manufacturers can offer, even for high power application, high computing power application. That is normal that for a server is working at high temperature for a very long time. Pretty sure that this can meet the customer requirements.
Okay, so that sounds good for me. So yeah, that was our last session, last question of this session. So then thank you very much, Jose and Carlos, for the interesting presentation. Yeah, it was a pleasure to have you here. And thank you also for your attention. Stay tuned. We have a lot of other webinars, other topics coming up. So then, yeah, just have a good day. Thank you and bye.
Thank you.
Thank you.